Okay, welcome back, everybody. Good morning. Welcome to the second lecture of Intelligent Systems. And today we are going to talk about uninformed search. As you can guess, what we are going to talk about tomorrow, which is informed search. And on Thursday, there will be adversarial search, where we have opponents doing something that we don't usually want them to do. But today we are just looking at systematic ways to search through the state spaces in which you can present many of the practical problems that AI agents are dealing with. Yeah. To start with, I was wondering of how many of you have looked into the game of Schnapsen. Can you raise your hands? Wow, I like you. Nice people, excellent. Because this is really important for the course. It's a game. Did anybody like it, actually? The more you play it, the better it gets. So I can promise you as well. Because then you start mastering the counting, you start mastering looking ahead, and so forth. And these are exactly some of the things that we're going to also implement in our programs. So keep up the good work. I'm really happy you took up the homework I gave you. And try to play the more strategies you think of yourself, the better you can later implement them into your game or investigate how the bots play. Did you start also trying to get the system up and running, the platform? Did anybody try? Okay, fewer people. Yesterday evening, I added, I had seen that I had forgotten to put this part online, but now there is also information about the final project and about how to get started. There was all somehow hidden in the modules, and now it is on the front page. There is one header where it says practical project and how to get started. So if you go to that page, you will see that there is a link to the Python version that you should get, the link to the GitHub where you can clone the code so that you can play around with it. It has a README, and in this README, it's explained how you use the API. So this is more than just the graphical interface. I showed you the graphical interface, which you can run. It's also explained in the README file in the Git. And if you just check it out, the repository, and you run the commands as they are given in the README, you should be able to start the visual interface and play against your own or against one of the bots we gave you. And if you also look at the README, you will also learn on how to access the platform in a programmatic way, so that you can write and change your own bots. So I think it makes sense to start looking into this platform as well in the next days. There will be help on Friday where the TAs can help you if you haven't been able to do the stuff that's in the milestone, which is also linked now and more clearly visible. So I think you can also now get started with the practical stuff. One final thing about those milestones, as I call them, or we call them, they have deadlines, and these deadlines are in the system, and I think they are this Friday for the first one, so have played around a bit with the platform. Next Tuesday is haven't implemented the first game bots. Then Friday after, I'm not sure about the precise deadlines, but those are more recommendations. So I really recommend you keep with this schedule. I will only check at the very end whether you have done all of them. So don't ask me whether it's okay if you hand them in a couple of days later. It is okay. It's your own schedule. You're grown-ups, so you should be able to organize in a way. These are recommended deadlines to work on. And if you do that, then you should be fine and prepared for working on the final assignment. The deadline for the final assignment, which is the Thursday of week 4, is really a hard deadline because we need to do the peer reviews on the day after. So if I don't have the papers, I cannot do the reviews. So you have to submit whatever you have you have to submit on the Thursday night of the fourth week. Yeah?
It says somewhere that the deadline for peer review is that is correct.
The deadline is on the in principle it's on the Friday night. You need a day for it.
It currently says 31st of February.
Oh, that's a typo. So it should be 31st of January. Oh, apologies. Where does it say that? In the
Yeah, in syllabus.
in the syllabus.
First part of the course overview.
Yeah, that should be one date. Okay, I'll fix that. So it's the day after, and you only need a couple of hours for these reviews. You know the stuff, you can read them, these papers very well, and then you write the reviews. It should be possible to do in this one day. Okay, so what I started out yesterday at the end of the lecture was to tell you that it's possible to represent many practical problems that we want to apply our agents on in what we call state space representations. And these are representations of the world where we have a state description for a certain situation the world is in, the relevant parts of the world for a certain problem are in, and where we can change from one of those situations the world is in, the so-called states, into other states by some actions that our engine, our agent takes. So basically, the problem that we have consists of some state the world is in, an initial state. We have many states in which the system can be, and then we have actions that get us from one state to another. And in the end, we want to find a state which adheres to our goal criteria. And in the end, that boils down to having these graphs of relations between states. And the problem finding, to find the problem means getting from the initial state to one of the goal states. So that is the simple idea. The states and the actions are atomic, so we can only do transition from one state to another, and nothing happens within the states themselves. So we don't do any calculations, we don't move. It's simply, all we do here is to look at the relations between the states, and the actions transform us to some other state, and we look within the search space and not within the spaces themselves. So this is sort of the basics of the state space representation, yeah?
Aren't the actions you can make a part of the state? Because you could really state different actions, but like the environment is the same, maybe we're in two separate states.
No, the idea of this representation is that the actions are really transporting you from one state of the world to another one. So you have the chessboard, you take an action, namely moving one of the figures, and then you end up in a new board position. And the board positions are your states.
But you put it like two different positions, but with different possible moves. You're trying to sensitive because you're not the same actions, but the position is the same.
Yes, there are different ways to get to the same states. So the state is not a tree, but it's a graph. So you can get from, I mean, if you remember the Hoover example, you could go back to the same state via some detour. So if you move right and you suck, and then you go left and you go up again, then you end up in a situation that you might have reached in a different way. But still, we have the spaces, and in this from these spaces, we can get to different spaces by some kind of action. And okay, so let's try to see how we can model a problem, a practical problem, using this state space paradigm. And the problem is the following. Imagine you have two jars. They are both empty in the beginning. One has room for 3 liters, one has room for 5 liters. And the goal is that you want, in one of the jars, you want 1 liter. And all you can do is that you fill the jar with fresh water, or you empty the jar into the other jar, or you fully empty it. Yeah? See the problem. We want to now, of course, we could write an ad hoc algorithm to solve this problem, but no, we want to translate this into a state space problem and then apply generic methods on the state spaces to solve this problem. So how do we represent this problem in a state space representation? Take a minute, think about it, maybe write something down, and then I'll show you, or I try. Okay, minutes over. So what would be a state in this representation? Give me an example. Let's not look at a mathematical construction yet, but give us an example. Yeah, you had an idea?
The big jar is empty.
Yeah? It's only half of the state, I guess.
Sorry?
It's only half of the state, I would say.
Yeah, okay, the big one's empty and the small one's empty.
Okay, so because we talk about liters, I interpret your emptiness as 0 liters, yeah? So we could represent this as this, yeah? What would be another state?
The goal state would be 1, 0 or 0, 1.
Okay, so I draw this, so this is 1, 0. No, okay. So these are 2 goal states. Anybody else with a goal state? Because I agree that these 2 are goal states, but they are not all goal states. Yeah? Up in the, yeah. That's an algorithmic way of solving the problem, but let's start from the representation in a state space, because we want to apply a generic algorithm that solves the problem. We'll get back to that. Yeah. 5-1 is also a solution. You also had something? Okay, so I had more. And 5-1 we had, I think you get the picture. So any state where a 1 is in one of the positions is a goal state. Do we have states which are not goal states? No. I should follow you. 14, you said. Okay, good. Okay, let's take the camera this side. Okay. Now we have the states, and I started to give you a hint the state we start. So how can we translate this now into state space system by, or a representation by also taking the actions into account? What are the actions? They're described in the goal here. What are the actions we can take? Yeah, yeah, up. Yeah, you.
Filling and emptying.
Okay, filling, emptying. Nothing. That you mean fully filling? Still completely filled to good, yeah. Okay. 2 more actions, Anybody? More actions? Yeah.
Filling one of the glasses with the other glass.
Okay. Left to right, maybe going to right it, or and then right to left. These are all the ones I can think of now. Anybody else? Let's see. I mean, it doesn't matter that much. Okay, so now we can write down the problem of filling these jars in a state space representation, because now we have all the actions. So I start with my initial state, and we have 4 actions. Yeah? So if we take action number 1, which is fill, there are 2 more I knew that because we have fill right, we have empty right, we have fill left, and we have empty. Yeah, so I was forgotten that when he said you can empty a jar, you can either empty the right one or the left one. Yeah, so now we have 6 actions. The first one is fill left. To which state do we get when we take this action, fill left? This? Yeah, it depends a bit whether the right one is the 5 or the left one is the 5. So let's say this is the one with 5 liters and this is the one with 3 liters, yeah? Just an agreement. Okay, so what are the, we have MTL. MTL, what do we have? Which state? What happens if you empty an empty jar? You're empty. Now just take this one off and make a this, yeah, because we end up in the same position. Fill the right. We have fill right. 0, 3. This one is again empty the right one. We get to 0, 0 again. Empty right. We have that one left to right. And we can, I think, delete both of them because they also go to the same. So that one would be empty right and empty left. Left to right and left to right, and this is right to left. Yeah, does it make sense? Are you still with me? Anybody lost? No, good. Okay, now we have these these two situations. And I draw it a bit further apart. We have F to the right, and we have 0 to 3. So what can we do here? And we just go through our list of all the actions that we can take, and then we get, if we fill left, what happens? What do we get? Exactly the same. So that's fill the left. Empty the left gets us, where does the empty left get us? Where does fill right get us? Empty right gets us also here, so this is also empty right. Then we have left to right. Does it get us to left to right? Yeah, so I could now also have drawn an arrow here. Yeah? Very good, yeah. So I was thinking of an action where you have the glass and you just fill it, empty it, and everything gets out. But you're right, you can just leave the 2 liters in here. And otherwise it would be very difficult to get to the 5-1 in the first place. I don't even know whether it was possible. Yeah? But we'll just continue with that. We now have still right to left. There nothing happens, that's also right to left, I think. If we have an empty jar and we fill it in the full one, nothing happens. So we have 2 more situations here. What happens here? We have fill the left one, gets us to 5, 3. Empty the left one, doesn't change anything. Fill the right one, doesn't change anything. I think you get the general picture. Yeah?
I think for empty left, it should be another loop on the left side.
On the left side.
Yeah.
Empty the left one means that we delete this one and we end up in 0, 0. Yeah. I mean, this is not about the details of this particular example. This is about you understanding how we can, in principle, now represent this problem about water and jugs in some kind of transition diagram between states. And whether you now have a drawing of this state as your representation or whether you have a mathematical tuple, doesn't really matter. What we do here is we look into states as some abstract objects and as abstraction, as transitions between the states based on some action that we choose as an abstract object. And now in the rest of the lecture, we're now trying to find how can we in these state space systems get as fast as possible from here to one of those states. Before we go to as fast as possible, because that's mostly tomorrow, we want to see whether we always find a solution, for example. So if you have such a state space, will you always find one if there exists one? And what is the algorithm to do that? And how complex is this algorithm? Yeah? So these are the questions that I asked you in the, when we built this system. So let's now look at a different game. And that is a very, very stupid card game. It's a simplified version of the card game Schnapsen for one player. So you don't have an opponent. And the game is as follows. You have one hand of cards. The player plays. And just one of the 5 cards that you have, you play. And you count the number of points that you have played. And you want to get to 20 or more as quickly as possible. That's all, yeah? So how can we represent this very simple, let's call it stupid card game in a state space representation? What's the state? Yeah?
The cards in your hand.
The cards in your hand. And I would also add the information about how many points you have on the table, I guess. Yeah? So you have 5 cards in the beginning. And you have 0 points on the table. Maybe you don't even need this in the state space, in the representation itself. What are the actions that we can have? Play a card. So how many actions do we have? 5. 5. So now we have new states, and these are now card decks again, but now with 4 cards. Yeah. How many of them? We have 5 of them. So what are the actions we can take? Again, is playing a card. So here we have now 4 options. Yeah? Okay, so this very simple game is exactly what you said here. We have a state space representation by just having the deck of cards as our states. Playing a card gets us to a new state because we have a new hand. We have different values. So if I start with this S, Jack, Ace, Jack, Queen, Ace, and King, we can play any of those 5 cards. So this is what I've represented here. We get a certain value for our state, which is the value 11. Because at the end, our goal is any of the states where this value is bigger than 20. That was the goal condition, that we check what is the value of the card deck and of the cards that have already been played, and that is 22 in this case. Yeah. So now, given a set of hand, obviously the problem is how do we find the best way of playing the cards so that we get to the 20 as quickly as possible? For humans, that is trivial because you just start with the valuable cards. You would just play the 2 aces and you know that you would be done. But for a computer and a generic state representation, it doesn't know anything about the value of the cards you have on hand. So in order to get to the one of the goals, we have different options and we don't know which one to prefer. So here you start, by coincidence, you start with the 11, with the ace, but then in the next move you start, because if that's the order you have gotten the cards with the jack, that's not very handy. Yeah. So I want to do Mentimeter. So if you would take out your telephones or computers, whatever you have, because I want to know something about this game from you, what you think the properties of this game are. So if you could go to menti.com, written up here, and use the code 261702. And then the question is, how many states do you need to maximally investigate to check all the possible solutions in this state space? So if we start in one position with 5 cards, how many different states are there that we can go to? Is it 16, 1,024, 54,000, or 120? Are there only 36 people participating, or are you still thinking? Still thinking, okay, good. Correct answer. What's that? What's this? So, that's correct. How do we get to this 120? Yeah, so you can do it mathematically. You can also just look at the picture. You know that in the first instance we have 5 choices. Then for each of the choices we have 4 cards that we can play, and you see it all. So the number of states we can have is 5 times 4 times 3 times 2, which is 120. Okay. Nice. I think I have another question to you, and that is, why is this number so relatively small, and what restricts the complexity in this case? And the answers are, the size of the state increases per level, the number of transitions decreases per level, the number of transitions increases per level, and the size of the state decreases per level. So I understand why most people say this, and it might be just a formulation of the question. So the size of the states doesn't change. The states are just the objects. What I think most of you understood is that the number of cards in a state decrease. But the number of states always is the same. The size of the states is always the same. The size of the states doesn't change. That's what we said, that the states are atomic. So it's the number of transitions that decreases. Because we have fewer cards, we only have 5 choices here, we have 4 choices here, we have 3 choices here. Yeah? So it's the number of transitions that is important for determining the complexity of these search spaces. So suppose now we have the situation where you get a card back from the stock. So you have the 5 cards, you play the 5 cards, you get a card back. And we do 5 rounds as well. Yeah? So how many states do you have to check after 5 levels, 5 tricks that you play, when you get a card back, when you refill? How big is the state space? Is it 100,000, 120, 3,000, 25, or 14,400? Okay. Again, you can look at take your combinatorics out of the mathematics book, or you can just look at the graph. And then we have 5 choices in the beginning. You get started back to you have 5 choices in the second step. In the third step, you have 5 cards. So your number of choices stays constant. So you have 5 times 5 is 5 to the power of 5. And that is 3,125. Okay, so let's move back to the lecture. We've answered those questions. So what you've seen is that it's the number of choices that you have that determine the state space, and it's called the branching factor. So we built this tree here. And the question is, how big is the tree? How many different options do I have? So that's the notion of a branching factor, and that is very much determining the complexity of the problem. So now we have, I think, a better understanding of how to get from a practical problem, be it cards, games, or filling jars, to a representation on which we can now apply generic algorithms, where we don't have to understand anything about cards, where we don't have to understand about the physics or so. The only thing is now we have to see whether we can find a path in this graph or tree that gets us from the begin state to one of the goal states. Yeah? And that is basically a search algorithm through a graph or a tree. And that means that decision making in these kind of problems is now reduced to some kind of search through a graph. And the algorithms that we're going to see there are very, very simple, so as compared to the algorithms that you've seen before. So this is really simple, but it's important to understand. But what we do, you remember the jar example where I built this very complicated graph. What you want to do is to translate this into a search tree, where you start from the root, that's the initial state of your tree, and then you build a tree where you create new nodes according to the possibilities of your state space. And building this tree, if you do it in a systematic way, you will arrive at a point where you either do not have any options anymore, or where one of the options in building these trees and the leaves will be the solution. Yeah? So basically, what we have, if we have this graph to start with, then we have our initial state, and we now draw the graph, as I did here, the tree, by going from the starting point to all of the possible nodes you can reach. So this is a complete state space, and you would never write it down in chess, for example, completely as a state space, because it's impossible. There are so many states. But what we can do is to develop a search tree on demand, which is a sort of a finite set of all this state graph. And if we do it in a good way, in the right way, then we can make sure that we find all the solutions, which are all the paths from the initial state to the goal. Yeah. So the task is now to start from one of those and build a tree that is as small as possible, that has the root, one of the start space, the initial space, and the initial state, sorry, and as leaf, one of the goal states. Yeah. So algorithmically, this looks like this. Again, as I said yesterday in the reader and on the slides, I always show the pseudocode, and I don't want to go into detail that much, but the idea is you start with the initial state of the problem, so this is the initialization of the tree, and then if if you don't have any, if you can't proceed anymore, if there's no action you can take from that state, you are done. And if you haven't found a solution so far, you can return that there is no solution. Otherwise, take one of the leaves that you have in the list and expand those by adding the new possible successors according to your state space. And if the node then contains the expansion, one of the children of the node that you have been expanding, if it's a solution, of course, you return it as a path, you are done. And otherwise, you call your procedure again recursively on each of the children that you've just expanded. Yeah? So if we start from the example that I had yesterday, the map of Romania, where you have a task of getting from Arad in a short amount of time to Bucharest, and you want the shortest path in terms of these distances, then all you have to do is to build a search tree from the state representation, where you say, okay, Arad is my initial state. What are the options that I can take? And then the options you can take are, of course, Zerint, Sibiu, Timișoara, and that is what you can see here. So we start with the initialized Arad, and then we choose the leaf to expand. We only have one because that was the initial state. We expand it by just adding all the three children, and then none of them is a solution. So we go on and now expand the children again. So we have to expand Sibiu, we have to expand Timișoara, and we have to expand Zerint. Yeah? And we do that until we either found a solution or we can't go any further. And this choice of, this should point to here. Choose the leaves to expand for expansion. That has dropped a bit. This is the one which determines the search process. Yeah. How do we add new nodes to this expansion list? Before I show you different ways of adding, building this expansion list, which leads to different search behaviors, I want to have a quick word to make sure the difference between the state space representation and the search tree is clear. So we have the representation of the state spaces, like I showed you before with the jars, which was this graph with where you can go back and you can go forward. And if you would like to describe the full problem, it would become huge. So we started, I think, with the two initial states, and then we had one layer of depth or two, and it was extremely complicated. Even the very simple example with the Hoover, with the 2 rooms, dirty or not, has already these 8 states. And if you have a more complicated problem, the state space itself is impossible to draw usually. The state is a representation. It stands for something physical. It stands for the 2 jars, and I've abbreviated it with some mathematical representation. But it stands for the 2 jars with some amount of water. The same holds here, the cards. The tree, on the other hand, is a purely mathematical construction that we built. So we have a node in the tree as part of the tree, and these two are really different things. The tree is built in order to find the map, the solution, the path, and the state representation is really a model of the world at a certain space. So if we now look at the tree search, then this looks obviously very similar to the representation that you would build, but be sure that these are 2 different things. So I maybe should have written down this in a different way, where these things are not now card representations anymore, but they are links to the card representations in the state spaces. Okay. As I said, now the most important thing in determining the nature of the search is how you expand the node. So when I find, when I'm in my search space and I need to expand the node, then I look at all the possible nodes that I can reach, and I have to choose one to start expanding in the next round. And this choice of which one to take first is what determines the search and also determines the possible success that we can have. Yeah? And these expansion algorithms then define what is breadth first search, depth first search, and so forth. And that is what we're going to look into in the second half of the lecture. So let's take 15 minutes break. Start 2 minutes before 12, and then we have enough time to look at all the search.
I don't know. Very silent. We have to cover it. Hey, guys. Yeah, so now we're going to go.
Is it niet met als u de twee sluit